Hello. Thanks for attending my talk. So I'm here to talk about Intra-Rack resource disaggregation and how photonics can make this happen more efficiently. I work at Berkeley National Lab, and we're blessed with having a supercomputer in the basement of our building that actually partially hits the building. It's pretty cool. But this gives us the opportunity to use it to figure out how scientific workloads use HPC systems. So we launched a study about a year ago in Cori when we only had Cori, so we didn't have Perl Matter, which means that Cori at the time ran all the open-size workloads that NERSC supports, open-size HPC workloads that the community runs. And then we tried to figure out, OK, so how are these workloads using the system? How efficiently are these resources actually being used? So this is a CDF, a cumulative density function. And the way to read this graph, and this is showing memory capacity for the Haswell and the KNL nodes in Cori. Cori had two types at the time. So the way to read this graph is if you follow that orange, red, that depends on the projector, I guess, but like that color line, and you start from the left, in that example that I've drawn here, so 75% of the time nodes use 17, Haswell nodes use 17% of the memory capacity, and KNL nodes use 50. So in other words, most of the time, only a fraction of the memory capacity is actually being used. Not surprising, other systems have found similar things, but this also holds true for all precise HPC workloads. Now, in our study, we also looked at other things. So here's an example of memory bandwidth, for instance. And this is only for Haswell. We only could instrument it for Haswell. And it is in two types of jobs, all jobs, that's the blue line, and the green line is basically not debug jobs, we try, but they're basically the same. And memory bandwidth is also underutilized. Now, we have to be a little careful with this one, because there's a long tail. Now, it's kind of hard to see with the lines. But there are memory bandwidth bursts, just that they're rare. But they do matter in terms of application performance. Now, in that study, we've looked at other things. I can give you some highlights relevant to this. Turns out jobs are predictable, and they're predictable early in their lifetime. And utilization of resources doesn't change much by average. Although I guess, again, there are bursts. So then we use this data to figure out, OK, so I have an imaginary rack of Cori, and now I want to reduce the resources in this rack because to reduce costs. So let's say, and that's the x-axis. So let's say that I'm starting to reduce the memory and the network, the NIC resources, by 10, 20, 30, 40%. Again, that's the x-axis. And the y-axis shows, OK, what is the probability that a CPU has to go to a different rack to find a resource? And we have three different types of resources: memory bandwidth, memory capacity, and NIC bandwidth, network bandwidth. So the point that this graph is making is about up to 50% of fewer resources. So I have half the memory, half the network resources inside the rack. The probability is very low. So we use this study to make this argument that we can get a lot of the benefit with just disaggregating resources inside the rack. We don't need to worry about the complexity and the cost of going across racks for disaggregation. And this is a much lower cost solution, and that's where photonics come in. So to give you the cartoon view, this is where we are today. We define nodes, and they are made of a certain configuration, CPUs, GPUs, memories, and so on. And we construct racks by basically copying and pasting. And now we have racks that have many of these nodes. But again, these nodes have the same type. Now, I know some systems have nodes of 2 types or 3 types, but still a few types. And managing these nodes and having users request exactly what node they want is not necessarily an easy thing. But what we'd like to move using photonics is this notion of I have a rack. It has resources. I don't care where they're located necessarily inside the rack. I just know that the rack has a bunch of resources, a pool of resources of different types. And according to what my workloads want at any particular time, I can pool and compose those resources into logical, we call them imaginary nodes. But the point is, I can allocate these nodes to jobs that need them and configure them as the jobs need them. So in this case, I have this logical node that has 4 GPUs, and my other 2 nodes, because the jobs don't use GPUs, have 2 CPUs or 1 CPU. It really depends on what the workload wants. What I'm trying to do here is I'm trying to reduce resource underutilization so I can have fewer resources. But do that inside the rack based on the study that I showed you before. So how does this is going to look like in the physical hardware? So we can divide our chips, our resources, GPUs, CPUs, and so on, into multi-chip modules. And you can have multi-chip modules have a type of chip each. So we can have a MCM with GPUs and MCM with CPUs. I'm not implying that I have one MCM only for each type. I can have multiple. But I'm saying that each MCM has only one type of chip. And I can have HBMs, custom accelerators, FPGAs, NVRAM. And there's going to be COM laser sources to provide the light, of course, and we have photonic interposers under those MCMs to provide the escape bandwidth. Now, we did this study, even with conservative assumptions based on what has been demonstrated, we can still get about 32 fibers out of an MCM, 64 wavelengths each. So that's pretty good bandwidth. And this is a benefit of photonics already. So we can take these MCMs and have multiple of them and have a photonic fabric in the middle and a small NIC, and we call that our node. And we put these on top of each other, and now this is a rack. We have these MCM-based nodes with these photonic switches and interconnects and interposers. Now we have a rack, and now we have the capability to have an optical path from any MCM to any other MCM, high bandwidth, low latency. Now, there's some considerations I don't have time to go into here, but there's questions. Okay, so what kind of optical switch do I want to use? Do I want to use like an all-to-all, an AWGR? Well, that's good because you don't have to reconfigure it, but it doesn't give you a lot of bandwidth from point A to point B. That could be, for example, like GPU to HBM, which would require high bandwidth often. Do I want to use special switches? Now, they give me high bandwidth from A to B, but you need to reconfigure them sometimes because they don't have many connected pairs. We can have intermediate solutions. But a question is, okay, so how do I co-design the rest of the system to support? Because what workloads want is not one thing, and it's also not really the extremes that I have in this first bullet. So how can I, for example, use architecture solutions to provide indirect routing for my all-to-all or efficient reconfiguration scheduling for my special switches? So there needs to be some sort of co-design with the system, and that's what we're looking at as well. Reconfiguration time for wave selecting and spatial switches, I mean, we've seen studies that quote anywhere from micro to milliseconds, or sometimes less for in academic papers, and that's great. But our workloads don't really change their requirements frequently, so that's not a high priority. Although it can be if there's a burst to memory and the switch is not configured to handle that. We think CXL can be used as the link protocol here. Now, latency is important. We have to tackle the bit error rate. Forward error correction can do that for us, but it is going to impose some latency. I'll get back to the latency question in a minute. But basically, with modern photonic leaks, we can meet all the design goals that we would need to implement this disaggregated rack. We can provide the bandwidth to each chip, so we don't restrain the bandwidth in and out of a chip, so we don't risk any performance degradation just from the bandwidth. Power is less than equivalent photonic switches. We can meet all design goals. Latency is a question. So there are two ways to look at the latency question. If we compare our disaggregated rack versus the rack we have today, yes, it is going to impact the performance of applications. We've seen that, not by a lot. I think the average was about 13% for CPU workloads with academic benchmark suites. It's not insignificant, of course, by any means. Now, we can scale up the system to make up for that in terms of system throughput. But the argument we're making here is, OK, we will probably have to move to some sort of disaggregated rack. So if we're not going to do it with photonics, how are we going to do it? We're going to do it with electronic switches. So turns out photonics, yeah, they do have latency overhead, but much less than modern electronic switches. So this is a speed up of a disaggregated rack implemented with photonics compared to a similar rack implemented with electronic switches. 5, got it. And I'm showing you 3 different kinds of test cases. The blue line is in order simple CPU. Out of order CPU is red, and then GPU is yellow. Now, on the Y, you have different benchmark suites. They're all multi-threaded, so HPC flavored. Careful with this big bars because they have both average and maximum. So the big bars tend to be the maximum one. And of course, some benchmarks, they don't run in all 3 cases. That's why you see, like, towards the right, you have only GPU benchmark and so on. But anyway, long story short, this disaggregated rack is still a lot faster than a similar disaggregated rack with electronic switches. And here we're comparing against the modern electronic switches, like the Anton 3s and PCI Gen 5s. So we see photonics as the technology to implement this disaggregated rack. Might actually end early. All right. Call to action. So we see photonics as something that enables system capability. It's great as a drop-in replacement in some cases, like the network and other parts, and that's wonderful. But we can also use photonics to implement things that were impractical before. Disaggregation is one example. And there are many ways to do it, of course, but we just described one way. But there could be other ways to use photonics to implement something new. And also, in terms of disaggregation and then how to co-design with photonics, software is a big deal. We could use schedulers, we could use program models, runtime systems, prediction for how workload is going to behave, programmability, APIs, all that. And I have a talk in a couple of hours that touches upon this, but it'd be hard to rely on proprietary schedulers for that, for example, just because we expect future systems to be heterogeneous and they won't look like one another. So it'd be nice to have some open source solutions of some of these problems so that then we can customize for different systems. And interoperability, that was just mentioned before. So if you want more information about the project that's behind this, you have a link below. I'll give you back 1 minute. I'm done early. Thank you.